G'day everyone. So I attempted to record a video and the audio was really bad, so I'm just going to go voice it over. All right, now this device, it measures the same type of thing as before in the last video, except for I'm only measuring the center conductor, which is the one that's kind of closest to the center of the circuit board, and then the shield, which is on the outside there. There is another loop, so I can form an imbalance with these cables because I cannot induce a magnetic field or some type of field that hits both these conductors together. So I'm just going to go put some current through the shield conductor by tapping off some input power and then having a secondary loop that will force current through the shield in the other direction. I've done this by having two 22 ohm resistors that go to the shields. So that's kind of a high impedance. It's a lot more than the differential, short circuit basically. And that will let me induce some different imbalances into this balanced transmission line. So that's the point. I'm trying to make some type of imbalance between a balanced transmission line. All right, I'm going to do the DC test now. So I'm going to hook up my probes, and there's two paths. Obviously, one of them is through the resistors through the shield, and the other one, when the switch is on, bypasses the resistors completely. It short circuits. The transformer there is a true one-to-one transformer. It is not a choke. There's two separate windings. They are not connected at all. So I turn it on, and you'll see that there's a little bit of power there going through the resistors, and they're heating up. And then I turn the switch on, and it'll send all the DC current through the transformer, which is why you get 4 amps there, and it shorts out the supply. So there's a quick description of the circuit there. I'm going to chuck a circuit diagram on the screen just so you can follow along about how this is connected. But I'll go grab the VNA and kind of show you that the through line is still mostly unaffected until you enable that secondary loop, which will then bring the 44 ohms across the input. And that will obviously drop the impedance down to about 20 ohms, and the SWR will change. All right, I've got my VNA connected, and you can see I'm doing an S21 measurement here. I do have a little issue with the cable, so I just fiddle with it for a second, and it comes good. So I'm losing about half a dB through the device, right? That's the current transformer stealing a little bit of current away, but most of the power is going straight into the S21 port of the VNA. Because that is a 50 ohm load. All right, so you can see I've got it still hooked up there. What I'll do is I open circuit on one of the sides here. So what I do is I open circuit the S21 port, and you can see that it's mostly an open circuit, so there's no weirdness going on, like an open is an open and a load is a load. I turn on the little secondary loop so you can measure that. Now that's the 22 ohms across the one-to-one, and when both of the loads are on, obviously you get 22 ohms or 25 ohms. So the SWR is about 2 to 1 because you've got two 50 ohm loads kind of hanging on the input there, which is about what you'd expect, right? Yeah, the power kind of is splitting between the two loads. All right, so I'm just going to take you over the setup again. It's the same as last video, basically. Got the Hacker F making the signal, QRPP amplifier, which makes about half a watt. This amplifier, which makes about 5 to 10 watts, goes through to our little device, which is measuring the shield and the center conductors. And it also does have that little, bypass loop when we turn it on. And then it goes over to a 50 dB attenuator through a 10 dB attenuator, and then you can see the tiny SA. It's just to verify that the signal's coming out the other end, and that there is amplifying the VFO leakage. That's 5 dBm there, so it's not really a big deal. All right, I will turn it on, and there we go. Now that we've turned it on, we can see that our currents are equal and opposite. Which is what you'd expect for a perfectly differential signal, which means all the power is going through over to that dummy load there, or attenuator, I should say. All right, so we're going to turn on that switch now. So we're going to enable the power back to the device. I'm going to try and turn it on without giving myself an RF burn, and we will see we got some funkiness there on the display. So what's happening is that the current through the shield is getting cancelled because the loop is trying to push the current the other way. So current on the shield is much lower. And the reason why the current on the center pin is lower is because we've split our power. So some of that would have been going through over to the attenuator to the dummy load is now going through those two resistors. So that's why our current's lower on both. All right, so this is Felstad, the program that I use. We'll do a live simulation and we can see that our currents are equal and opposite. We're measuring with these 10 ohm resistors here. These are the two little transformers right at the SMA port of the input. Now, when we enable this, we'll see our shield current, which is red, decrease a lot, and our center conductor decrease a little bit. So this is trying to backfeed through the shield. So the shield current kind of cancels out, and the center current does drop a little bit as well, because instead of just going straight to the 50 ohm load, it now has to also go through this one-to-one transformer. All right, we're going to do the same trick as last time. We are going to close up the core while it's running. So you can see that's the tried to be cancelled current. Now, if I try and force the currents to be equal by giving it this little toroid, you can see that it does try to work, but this is not a very good toroid, right? It's only a single clip-on ferrite, so they're not completely balanced, but it is a lot better. And if you had a proper, 30 dB common mode rejection ratio balun, those two currents there would be equal and opposite. All right, so yeah, that was some pretty fun testing. I really have to figure out a better way of capturing better audio with the phone because I'm no good at voiceovers, as you can tell. But it was fun playing with this stuff and trying to figure out how can I demonstrate what I want to show. I might try the actual common mode current method in the next video. I know how to induce it. I'm going to use a center tap transformer and a center tapped load, and that should induce common mode current equally into both the wires rather than just forcing current through the shield like what I was doing. But anyway, yeah, let me know what you think. 7-3 all, VK4 Delta Lima.